I welcome you to today's lesson on algebra. The topic of today's lesson is principal ideal domains, unique factorization domains and Euclidean domain. You may recall the fundamental theorem on arithmetic. It says that if you have a positive integer, it can be factorized into a product of primes uniquely. For example, if you take the positive number 72, which is an integer, it is 8 into 9 and it is also equal to 2 cube into 3 square. So, we have 72 is equal to 2 cube into 3 square. Here 2 and 3 are primes and 2 cube into 3 square is a product of primes, and this representation for 72 is unique. And today our objective is to generalize this fundamental theorem of arithmetic to a general setting. To do this, we proceed as follows. We define classes called principal ideal domain PID, unique factorization domain UFD and Euclidean domain ED. So, first we define these three classes and we look at some examples and some non-examples, and then we look at the connection among these three domains. Let us start with the definition of principal ideal domain. We abbreviate this principal ideal domain as PID. Principal ideal domain is an integral domain in which every ideal is principal. We may recall that an integral domain is a commutative ring with unity in which we do not have any zero divisors. And so, if we have an integral domain in which every ideal is principal, by principal we mean that ideal should be generated by a single element. If that is the case for each and every ideal of an integral domain, we call that integral domain a PID, principal ideal domain. Let us look at an example. The ring G of integers is a PID, that is the set consisting of 0, 1, 2, 3 and so on, minus 1, minus 2, minus 3 and so on is known to be a ring, and we can see that in this ring all these conditions of this definition are satisfied. Therefore, ring G of integers can be seen to be a PID. To give a non-example, we can consider the set G of x. G of x is the set of polynomials whose coefficients come from the set of integers, and we can see that this is not a PID, means in fact we produce an ideal of G of x which is not principal. To do this, we consider this ideal I defined as a naught, defined as the set consisting of a naught plus a1x plus and so on plus a n x power n belonging to G of x, such that this constant term a naught is even and n is a non-negative integer, and we can see that this ideal is not principal. This set G of x cannot be a PID. Next, we make definition of the unique factorization domain. This we abbreviate as UFD. This is also an integral domain satisfying these following two conditions. Every non-zero and non-invertible element of R where an integral domain R is taken, in that every non-zero non-invertible element R should be expressed as a finite product of irreducible elements of R. And then if P1, P2 and Pn and Q1, Q2 and Qm are irreducible elements of R, such that the product of Pn's and the product of Qm's, that is the product P1, P2 and P into Pn is equal to product Q1, Q2 up to Qm, then if we can obtain that n is m and that there is a permutation f of the set consisting of the first n integers, such that Pi and QFI are associates of each other for each I between 1 and n. If these two conditions are satisfied, we can show that we call that integral domain a unique factorization domain. These two conditions in fact tell us that every non-zero non-invertible element of R can be uniquely expressed as a product of irreducible elements of R. This is something like the prime factorization theorem in arithmetic. There we saw that every positive integer can be factorized into a product of primes uniquely. So, this is a generalization of that. Now, let us look at examples and non-examples of unique factorization domains. After making the definition of UFD, let us look at some examples of UFDs and then some non-examples of UFDs. The ring G of integers can be seen to be a UFD. In fact, shortly we will prove that every PID is a UFD because this G becomes a PID. We can also see that G is also a unique factorization domain. For a non-example, we have two integral domains. Let us consider one of these, that is, the G of square root of minus 5 is not a unique factorization domain. This is an integral domain. So, here we will produce some irreducible factors, irreducible elements. They are 3, 2 plus square root of minus 5, 2 minus square root of minus 5. These are irreducible in the set G of square root of minus 5, and we have 3 into 3 is 9, and 9 is also equal to 2 plus square root of minus 5 into 2 minus square root of minus 5. This is a plus b into a minus b, product is a square minus b square, that is 2 square minus of minus 5, that is 4 plus 5, that is 9. And these two, 3 into 3 and 2 plus square root of minus 5 into 2 minus square root of minus 5 are distinct representations of 9 as product of irreducible elements. And we can say that this irreducible element 2 plus square root of minus 5 cannot divide 3. For this G of square root of minus 5 to become a UFD, every non-zero non-invertible element should be uniquely factorized into product of irreducible elements, and such that these factorizations should be equivalent up to order and associates. Means, if we can get 2 plus square root of minus 5, 2 plus square root of minus 5 and 2 minus square root of minus 5 are associates of 3, and conversely 3 is an associate of these two, then this is a valid factorization. But 2 plus square root of minus 5 is not a divisor of 3, means these factors are, these irreducible factors are not associates. So, this violates the second condition in the definition of UFD. Therefore, G of square root of minus 5 is not a UFD. So, this integral domain can also be seen to be a non-PID, because later we will be able to show that every PID is a UFD, because if we have a set which is not UFD, it also becomes a non-PID. Therefore, this also works out to be an example for a class which is not PID. Next, we define the class of Euclidean domains. To be precise, we define a Euclidean domain. Let R be an integral domain and n the set of positive integers. R is said to be Euclidean domain if there exists a mapping G from the set of non-zero elements of this ring, that is R minus singleton 0, to the set of integers, such that G of AB is G of A into G of B. G preserves the products for any AB coming from the set of non-zero elements of R, and for any AB in R with B non-zero, there exist elements q and small r in capital R such that A is equal to QB plus small r, and the small r is either 0 or G of either 0 or G of R is less than G of B. This is something like the Euclidean algorithm that we study in arithmetic, and here G is called a Euclidean evaluation or gauge function, and Q and R are called quotient and remainder respectively. You may recall from our arithmetic, if you have any two positive integers, for example 17 and 5, you have 17 is equal to 3 into 5 plus 2, 5 is non-zero. If you divide 17 by 5, 3 is quotient and 2 is remainder. So, this is a general setting of our unique factorization, our Euclidean algorithm to integral domains. Now, let us look at an example and a non-example of Euclidean domain. The ring G of integers is a Euclidean domain with the gauge function G of n as modulus of n, and in fact any field can be seen to be a Euclidean domain if the gauge function is taken as G of n is equal to 1 for all n coming from the field, or rather G of A is equal to 1 for all A coming from the field F. The ring of Gaussian integers is also a Euclidean domain. You may recall that the set of Gaussian integers is a ring, and it is in fact the set of numbers of the form a plus ib, where a and b are integers and I is square root of minus 1. That is the ring of integers. We can see that it is a Euclidean domain. So far we have defined the classes Euclidean domains, principal ideal domains, and unique factorization domains. Let us denote them by E, P, U respectively. The class of Euclidean domains is subset of the class of principal ideal domains, means we can show that every Euclidean domain is a principal ideal domain. We can further show that every principal ideal domain is also a unique factorization domain, means the class of principal ideal domains is a subclass of unique factorization domains, and all these are integral domains, and the class of integral domains is denoted by capital I, and the class of fields is denoted by capital F, and we can show that every field is a Euclidean domain, and all these are integral domains. So, U is subset of I, the class of integral domains. The question is, can in any one of these equality take place? Means, do we have the reverse inclusion? We are saying that every field is a Euclidean domain, and conversely, can we have that every Euclidean domain is a field, and we have certain Euclidean domains which are not fields. So, this inclusion is strictly proper, means we have a Euclidean domain which is not a field, means this inclusion is strictly proper inclusion, means F is strictly a subset of E. Similarly, we can also show that we have a principal ideal domain which is not a Euclidean domain. So, we have E is strictly a proper subset of P. We can also show that we have a unique factorization domain which is not a principal ideal domain. So, this inclusion also becomes a strict inclusion, and we can also show that we have an integral domain which is not a unique factorization domain, means this inclusion also becomes a strictly proper inclusion. Let us look into these hierarchical inclusion properties. Before that, what we are trying to show is F is contained in U, E is contained in P, is contained in U, is contained in I with this Venn diagram. F is the class of fields, E is the class of Euclidean domains, P is the class of principal ideal domains, U is the class of unique factorization domains, and I is the class of integral domains. We want to show that F sits inside E, and E sits inside P, and P sits inside U, and U sits inside I. and we can give examples of integral domains which are not UFDs, and we can give examples of UFDs which are not PIDs. We can give examples of PIDs which are not Euclidean domains, and we can give example of Euclidean domain which is not a field. So these inclusions also become strictly proper. Let us start with this inclusion theorem. Every Euclidean domain is a principal ideal domain. Every Euclidean domain is that integral domain in which we have a Gauss function g on that Euclidean domain into n, satisfying g of a b is g of a g of b, and we have Euclidean algorithm like property. So let us start with an integral domain R, and let us assume that it is a ED, a Euclidean domain, and we want to show that this is a principal ideal domain. Let us recall what a PID is. A PID is an integral domain in which every ideal is principal. So let us start with an ideal of R. Let us take capital I to be an ideal of capital R. We want to prove that this capital I is principal. By principal we mean it is generated by a single element of R. That is, we want to obtain that I is the ideal generated by an element A coming from capital R, and this ideal is not the trivial ideal, that is singleton 0. If it is so, it is generated by 0, that ideal is generated by 0 and it becomes principal. So let us assume that I is not the trivial ideal singleton 0. So there is at least one element in I different from 0, and now we look at all the non-zero elements of capital I. Let us say they are small a's, and on them we apply the Gauss function coming from the Euclidean domain G, and we look at g of a. G is a mapping from R into the set of natural numbers. So g of a is a natural number, and we are collecting the images of G on the non-zero elements of capital I. So this set of such GAs is a set of natural numbers, and because this I is having at least one non-zero element, this S is having at least one element g of a. So S is non-empty set of positive integers, and these are all positive integers, and therefore these are bounded below by 0, and we have the well ordering principle to the non-empty set of numbers bounded below. It says it has at least one least element. The well ordering principle says for S that it has at least one least element because this S is bounded below by 0. Let us choose an element A in capital I. A is non-zero such that g of A is the least for S. This exists from the well ordering principle, and we have A is coming from capital I, and therefore the ideal generated by A is contained in the ideal capital I. If you small a is coming from capital I, and if you multiply A from any element R, from small r from capital R, A into small r is also contained in A into small r also belongs to capital I because capital I itself is an ideal, and small a belongs to capital I and small r is coming from capital R. Therefore, from the field property you can show that this ideal is contained in ideal capital I. We want to prove that this capital I is in fact equal to the ideal generated by small a. So let us take an element small b from capital I. We want to show that this small b is a member of the ideal generated by small a. Here we apply the division algorithm. This comes from the property of Euclidean domain. This b and a are here becoming non-zero numbers, and from the Euclidean algorithm like property we have b is equal to qa plus r, where r is 0 or g of r is less than g of a. This is coming from the definition of Euclidean domain. And from here, if R is not equal to 0, then we have R is equal to B minus Q A, and this small r is coming from capital I, and if R is non-zero, we have G of R is less than G of A, and we have an element R coming from I, and because R is non-zero, this belongs to the set capital S, and further we have G of R is less than G of A. Therefore, this small r belongs to capital S with its G value less than G of A, but this violates the condition that G of A is the least such value. Therefore, R has to become 0, means B minus QA is 0, therefore B becomes QA. B is a product obtained by multiplying small a with an element from capital R, and therefore this has to belong to the ideal generated by A. Therefore, B is a member in the ideal generated by A. We started small b coming from capital I, small b is any general element, therefore capital I becomes a subset of the ideal generated by A. Thus, the ideal generated by A becomes equal to capital I. So, we started with an ideal, and for that we could obtain an element which generates that ideal, means we are able to show that ideal is principal. Thus, we have that every Euclidean domain is a principal ideal domain. Next, we will obtain another result which gives the inclusion that every PID is a UFD, means every principal ideal domain is also a unique factorization domain. So, let us start with a PID. Let R be a principal ideal domain. We want to show that this is a UFD, means for every non-zero non-invertible element small a of R, we should obtain a unique factorization of irreducible factors equivalent up to associates and orders. So, let us start with a non-zero element and non-invertible element small a from capital R, and we can obtain a prime number P1 in capital R such that P1 divides A. This comes from the property of principal ideal domain. A is coming from capital R, means P1 is a factor of A. Therefore, we have A is equal to P1 into A1 for some A1 coming from capital R, and this small a is non-zero. So, this small a1 also becomes non-zero, and we have the ideal generated by small a is contained in the ideal generated by small a1, because if you multiply small a by any element small r from capital R, a into small r is equal to P1 a1 into small r, that becomes R P1 a1, and that becomes an element here in the ideal generated by a1. Therefore, the ideal generated by A is sitting inside the ideal generated by A1, and this P1 is invertible because it is prime. And if in case equality holds in this inclusion, we have A1 is equal to some x into A. A1 will be a member here, therefore, it is an x into A where x is coming from capital R, and from this we obtain A is P1 A1, and for A1 we can take x into A, and this is further equal to A into P1 into x from commutativity. And therefore, and if we cancel A's, which is non-zero on both sides, we have one is P1x, and from here we obtain that P1 is invertible, and this contradicts that P1 is not invertible. Therefore, equality does not hold here. Therefore, this cannot be equal to this, means you have an element here which is not here, therefore strict inclusion takes place here. So, we have ideal generated by A is strictly contained in ideal generated by A1. If A1 is invertible, then A and P1 are associates, and hence A itself is prime. From here P1 becomes an associate of A, and if you have A1 inverse A is equal to P1, A becomes an associate of P1. Thus A and P1 become associates, and we also have A is prime. So if A1 is not invertible, we can repeat the procedure that we have applied before and obtain that A1 is contained in the ideal A2 in a proper way. And this process can be continued to obtain an ideal AN to contain an ideal AN minus 1 such that AN minus 1 is equal to Pn into AN. This continues as long as AN is not invertible, but our integral domain R is a PID, therefore this sequence cannot go indefinitely. So let us assume that the ideal generated by AN is equal to R, and here this is, we have A is P1 A1 and A1 is P2 A2 and A2 is P3 A3 and so on, AN minus 1 is Pn AN. So we have these equalities. All these P1, P2, P3 up to Pn are primes and AN becomes invertible. And because Pn is prime, we can see that this also is prime, Pn AN is also prime, and for Pn AN we write Pn prime. So in place of Pn AN we can write Pn prime, which is also a prime, therefore A is obtained as product of primes. All these P1, P2 up to Pn minus 1 are primes and Pn dash is also a prime, therefore we are able to express A as a product of primes. Thus every PID becomes a UFD. In this lesson we have defined principal ideal domains, unique factorization domains and Euclidean domains, and we showed that every principal ideal domain is a unique factorization domain. We further showed that every Euclidean domain is also a principal ideal domain, that is, the class of Euclidean domains is a subclass of principal ideal domains. That is, we tried to generalize the concept of Euclidean algorithm to a general setting.